Moja, we start? Okay. All right. So, dear all, and welcome everybody. I would like to welcome to this third online seminar that belongs basically to a series of seminars of the Journal of Resilient Cities and Structures. And I assume that if you are listening to this seminar or either online or recorded, you are familiar with the journal. However, I strongly encourage you to submit manuscript to this new journal that is growing really fast and is going to be really a reference journals in the field of resilience internationally. And right now, the journals allow open access publication, so this is a kind of interest and opportunities because there is no fee to publish in the journal right now. So today's seminars is from performance-based design to resilience-based design of city. And the seminar will be presented by Professor Stojadinovic, who is professor at ETH and is also chair of the Structural Dynamics and Earthquake Engineering Group at ETH, as well as a member of the ETH Risk Center. He graduated from the University of Berkeley with a PhD in 1995. And he was professor at University of Michigan first, and then University of California, Berkeley, before joining ETH in 2011. He is an ACI fellow and recipient of the 2004 ACE Walter Huber Civil Engineering Research Prize, and in the 2017 also of the ACI Cester Paul Sees Award for Excellent Instructional Research. Professor Stojadinovic main research is in the field of community disaster resilience, focusing on performance-based probabilistic resilience evaluation and design of civil infrastructure system, buildings, and bridge. He has also performed some research in performance-based design principle to develop new response modification technique, such as rocking for seismic protection of civil infrastructure assets, and to develop new methods for seismic design of structures. The third research activities of Professor Stojadinovic is also focusing on multi-physics and stochastic extension of hybrid simulation methods for the evaluation of the response of civil structure to dynamics excitation using hybrid models. Currently, he has published more than 350 publications, and he has graduated 43 PhD students. So, we are looking forward to this very interesting presentation today, and without any further ado, I will leave the floor to Professor Stojadinovic. Thank you.
Thank you, Gianpaolo. Thank you, Ying and Michelle, the editors, the chief editors of the Resilient Cities and Structure Journal, for inviting me to give this presentation. I will try to not only tell you what my group is doing, but again, as Gianpaolo said, encourage everybody to consider the research in the scope of cities and structures and submit a good paper to the journal. So let me go ahead and move to my first slide, the title slide, if I hopefully can soon. It is going to be a presentation on the topic of performance-based and resilience-based design. What I want to emphasize is how we can transition from the design of buildings, single ones that we have done quite a bit, to the design of cities, and how the objectives of that design will change. So some 20, 25 years ago, maybe even 30 years ago, we started thinking about performance-based design of structures. And here you see a very old picture of the performance states of some typical building somewhere, the operational, the immediate occupancy, the life safety, and the collapse prevention ones, and the continuity of this damage, as well as the continuity of consequences of an earthquake in terms of the casualties, in terms of the direct damage, and in terms of the indirect damage that we suffer often in large events, in rare events. And performance-based design was initiated this idea centers around the technology neutral design that doesn't rely on a particular reinforced concrete or steel or timber or base isolated solution, but aims to achieve performance objectives, perhaps one, perhaps more, that are related to the seismic risk exposure of the structure itself. So this is the essence, the essential idea of performance-based design. And the way we do it is that we consider a number of performance objectives associated with risk, with the hazard exposure that the building may have, differentiate, of course, between the buildings. But then for the design situation, we select the design hazard, we select the acceptable response limits as to how that define the performance, and then we use a very normal standard design iteration that starts with the trial design, evaluates that design in terms of the attained performance, and then we judge if we're satisfied or not. If not, then we go back and improve the performance of the trial design, and then try again until we actually get a good design that satisfies these desired performance objective or objectives. And so this works. This works, and we see that by comparing recent and not too far in the past earthquakes. And here is an example from Mexico City that suffered two similar earthquakes, similar in magnitude and location, in 85 and 2007. And it is a very, very remarkable difference in terms of the performance of the city and the performance of the individual buildings, and especially so in terms of the casualty counts. And we see improvements not only immediately because of the immediately adopted new code, but also as we go forward in time and get better and better buildings. But this is a sign, this is a good sign that we can address this collapse prevention performance objective. But as we went forward in research, especially in practice also, we see that there is a variety of performance objectives that we can look at. Casualty risk is one. Chances of the building being unoccupiable, downtime is expected, building cost, the initial one, and the repair cost, and you see how they are inverse from each other. And we have recently even started looking at the carbon impact of the initial building cost and the repairs within the same performance-based framework, meaning that the scope of the possible performance objectives here has increased. And clearly, of course, the scope of possible structural solutions has widened in many ways. But this is the statement of the power of the performance-based earthquake engineering framework that was this particular one conceptualized at the Pacific Earthquake Engineering Research Center. But at the time, the MAE and the MCR Center were also very active and working along the same line of starting with the exposure of the building, looking at what is the information about the facility, then looking at the hazard that this structure is exposed to in terms of probabilistic description of that hazard, and a variety of different intensities associated with different probabilities of exceedance, and then jumping into a risk evaluation that starts with a structural analysis in terms of engineering demand parameters, looks at the capacities and the resulting damage, and then evaluates the losses, either direct ones in terms of the lost building or casualties even, and the possible repair cost, as well as the indirect losses in terms of the downtime and inability to use and offer service in that facility. But overall, the performance-based engineering framework started to consider multiple performance objectives and facilitate decision-making in the probabilistic sense. This is a very important step forward. It took a while. It took, as I said, 25, 30 years to get here, but it is being adopted in practice. And what we have seen in the recent earthquakes is this progress towards preventing collapse, but still some buildings fail. And to recover after an earthquake, we need to rebuild these kinds of buildings. Most likely, we need to start from a completely new structure. However, when we have something less of a severe performance of that building, then we can indulge and undertake repairs. And especially when consider carbon laws that we imposed by rebuilding, a repair may be a very attractive option, not only financially, but perhaps also from many other performance views. We repair structural elements and systems, of course, but also the non-structural elements that suffer damage. And then if the building is not as damaged or repaired, we start to restore its function. We repair the equipment, the infrastructure, the service connections, and go on to restoring the functions of that building in terms of turning the lights on, the water on, the communications on, the air conditioning and heating on there, and bringing the big building back to life, attracting people back to the building. However, we have seen in the past earthquakes, especially when there is much more repairs than tragic death recovery, that the path to recovery is quite long, depending on the damage state, of course, but longer the bigger the damage state is, because there are quite a few preparatory tasks that one has to make and do and complete before any of the repairs can start. And here we always start with some rapid inspection in terms of tagging and occupancy immediately after an earthquake, but then we have a detailed inspection, perhaps some cleanup. Definitely we need to go into consideration of what repairs can be done, what needs to be done, and design that, estimate the cost, find the contractors, find the financiers, obtain finally the permits, mobilize the contractors with their materials and equipment and people who are going to work, and only then start the actual repairs. So there is quite a chain of impeding factors that Mary Comelio identified in the mid-80s, but this chain is here now, very visible, and we can dissect it into particular elements and see how to work with it. And this is a step that is very, very necessary when we want to model the recovery of structures. And we can build on the performance-based engineering framework, perhaps the FEMA P58 incarnation thereof, and add another analysis of the functionality of the building, perhaps using fault trees, look at the mobilization time, the time that is required to overcome the impeding factors, look at the repair time that is needed to restore the building to the level when the lights can be turned on and the function of the building restored and returned to previous state, pre-earthquake state. And this framework, the one that I choose to present here, is the EFREC framework that Dr. Vesna Terzic developed originally, and then somehow we collaborated, and I'll talk about this a little bit later at a later stage. But this is a framework that models and simulates the repair and function restoration processes of a building. And it is a very detailed one. It allows one to put together a repair plan in terms of the sequence of the repairs of the structural and non-structural components. Here in this example of a 42-story building in Los Angeles, there is a set of Gantt charts that addresses particular elements such as shear walls, structural elements, non-structural elements such as elevators, service level elements such as partition walls, cooling, and conditioning. In time, as the progress of this work goes on floor by floor in this tall building. And also what we can see what limited resources in terms of material, machinery, and manpower for recovery can do to prolong the recovery timeline. The recovery timeline is already almost a year, and with limited resources or some kind of additional impeding factors during the repair process, they may get even longer. But what is very important for design purposes is that we can quantify, measure this repair process using the well-known resilience curve, the swoosh-shaped curve that starts with a drop of functionality and a time to decide what to do with the building, time for impeding factors, and then the process of the recovery that gradually starts and then builds up towards restoring the function of this particular structure. Having this process, the framework, the ability to analyze recovery in a very good detail, we can quantify it using the resilience curve. And that gives us an opportunity to extend the peer performance-based engineering framework by inserting the recovery process simulation here between the risk and the loss assessment. And so now the loss assessment includes this time dimension. It includes a very good estimate of the time needed to recover, of the cost needed to recover, and of the resources needed to do so, or either to absorb the impeding factors, to take care of them, or to affect the actual repairs. So the scope of decision making is now much broader, and yes, more complicated, but also more realistic. Especially so looking at the modern earthquakes happening in modern communities, in modern cities that have advanced in terms of protection against collapse and are now not suffering as much in that sense, but still suffer quite a lot in direct and indirect losses to the buildings in them. And speaking of cities, let's go to that level now. A city is a complex system. A city is a system of systems, of houses and infrastructures, the technical systems, but also city is about people, and not also first and foremost, the city is about people and the interaction that these people have with the technical systems that serve them in the city. This is a socio-technical system of systems. And as such, we have to look, when we want to look at resilience-based design, we have to look at the elements of the system. The main reason is that the recovery of a single structure, no matter how masterful we are at that, and performance-based design of that structure, does not happen in a vacuum. Here is an example from Christchurch, where the central business district was quite damaged in the 2011-12 series of earthquakes. But it was cordoned off for a while until the impeding factors and the planning was completed, until the financing was done. And then slowly the cordons were lifted as the buildings became available for repairs and finally repaired or replaced and returned back to function so that the life in this downtown could come back to approach the normal pre-earthquake life. So recovery induces of the housing and infrastructure, induces multiple interdependencies that we have to consider when we move from consideration of a single structure to the consideration of a city. Here is an example. We can have casualties and injuries right after an earthquake, and they will present a load of the emergency services somewhere in the city. Further, housing damage widespread in the city represents demands on temporary housing and repair resources. Temporary housing immediately, repair resources after slightly after the impeding factors are overcome. But on the other hand, lack of housing or people moving out reduces the demand for infrastructure systems. So those systems have some time to recover and repair and restart their services because the demand for their services is not that high. In the meantime, as the recovery gains pace, there may be competition for recovery resources, introducing a further level of interdependency. And finally, and most importantly, the people in this stricken region, the city, make decisions about what they're going to do. Are they going to evacuate or remain? And those decisions clearly affect what the housing is doing and how that housing affects the other systems that are in the city. So looking at the recovery of the city cannot work without considering these independencies. Recovery is a regional problem. The single structure depends on other structures. So the hazard and risk exposure, hazard assessment and risk exposure become regional. The infrastructure systems get immediately involved. The recovery of the technical systems plays a role in the recovery of the city very, very clearly. And there are very, very important interactions between the individual actions and the collective actions of the citizens. And not only in how they solve their own problems, individual problems, but how they restore the workings of the city at the level of at several societal levels that are higher up above the personal safety and well-being of a person. So to formulate resilience-based design of a city, we have to include a notion of technology-neutral design, building on performance-based design principles, and also address several performance objectives simultaneously, but those are now related to the risk and recovery of the city, not of a single building. Considering that city as a socio-technical system of systems with all of the interdependencies involved. Therefore, the resilience-based design problem is more complex. To solve this complexity, we need a really good model. And what we have been developing in EDH for a while now are models that look at the city as a system of systems and employ flow models to represent the flow of resources within one infrastructure system and between infrastructure systems. The components in these systems, including housing, can be damaged, and as they are, they disrupt the function of these systems. But they are repaired in some repair sequence, and they restore their functions gradually through the recovery process. This induces an evolution of the infrastructure system level demand and supply and ability of that system to function and satisfy the needs that may exist in the city, in the system of systems at any point in time during the recovery process. By this supply and demand interchange for every of these elements, and because we have a system operation model, we can look at how how the interaction between the different systems affects each other and how the interdependencies occur during the recovery process and what are the consequences of those interdependencies. So the flow model and the supply and the demand paradigm have been very helpful for us because we didn't need to explicitly instate the interdependencies between different systems, usually using a layered model with some links going vertically between the layers. But the interdependencies appear organically because each system at every point in time of the simulation tries to satisfy their demands from the available supplies using the links that are available and operational at that point in time within the capacity of the supply that is available at that point in time. So it is what I consider a nice model, but it's not the only one. It is important that interdependencies are captured. And the model that I talk about is this iRecodes framework. This is the model that we have at ETH that simulates the infrastructure system of systems recovery process. And it enables us to look at the operation, supply, and demand time history, captured in dependencies on the operation side, but also it enables us to look at the recovery resources, the material, machinery, and manpower that are involved in the recovery process. Also, the manpower, finance, and decision-making effort, permitting effort that is required to overcome the impeding factors to the start of the actual repairs. And this dual operation and recovery view of the supply and demand is another important step in the iRecodes framework. It enables us to look at and quantify the recovery process again using these swoosh-shaped resilience curves, starting with the drop of service and recovery of it, and due to the presence of interdependencies, identify regions like this, where the interdependencies, the connections between the water, power, and communication system in this case, induce additional drop in functionality and inability to satisfy the demand. There is a larger unmet demand. And so what we did next, and that is where we started to collaborate with Dr. Vesna Terzic, the ETH side with RICOS, her side with EPREC, is to see how this whole thing can come together in a performance-based like analysis of a city. There, we recognize that we have multiple buildings and multiple infrastructure systems. The buildings are represented in EFREC as individual analysis, therefore this exponent n, and the infrastructure system is already represented in IRE codes. So the system, the analysis framework starts with the hazard analysis, just like the PBE framework, the structural analysis to figure out what the damage is, but now that is done for multiple buildings at the same time, and then multiple buildings are assessed for their recovery trajectories using EFREC. This is then integrated in RICODES, both in terms of the recovery resources and the functional recovery of the infrastructure systems. So both the buildings and the systems are treated in parallel at every time step of the IRE-CODES recovery analysis. And that, in the end, produces a city-level estimate of what it will take for it to recover. So here is an example from the downtown San Francisco fictitious earthquake affecting several thousand buildings in these number of blocks that form downtown San Francisco business district and a little bit here towards the marina. And just using some typical buildings, tall ones, medium-rise ones, and short ones, we simulated the recovery, and one can see how stepwise recovery story by story takes place in terms of building function, with short buildings recovering faster, of course, than the very tall ones. But there are other things that we can see, because we consider recovery resource also is the demand for workers. And the supply for workers is this line here, where the demand is this jagged line indicating the variability of the demand for workers once buildings get ready for the actual repair, once buildings overcome the impeding factors. And these blue areas here are areas where the current supply of workers is insufficient to meet the demand, and therefore causing further delays in the recovery process. For example, this jump here. So this is a very valuable analysis and showing that the combination of EFREC and IRE-CODES can be a very, very nice regional recovery analysis tool, helping make decisions in real time, helping make projections for what the future earthquakes may do. One additional aspect, and very important aspect, is the view of what people do and how people reconstitute their lives and how they reconstitute the societal functions of a city. Individual citizens make choices, whether they will reoccupy the house where they used to or not, where they will live, when they will restart using the infrastructure systems, and how this demand will be reflected on the systems, and also how they will come back to life in this city. If they're nurses, they can come back to work in hospitals. If they're teachers, they can come back to work in schools. If they are hairdressers, they can come back and service their customers. If they are workers in factories or government or financial services, they can restart everything that constitutes an economic activity of a city. The model that we use to do this is based on the capabilities approach by Sen and Nussbaum. This approach looks at commodities. That is, what are the resources that enable a person to fulfill their capabilities. And the capabilities are what that person may want to do. The conversion factors are simply existence of a house, operation of an infrastructure system at a very basic level, and then further operation of the hospital, school, businesses, and so on. And then there is the agency and choice of a person that, given the particular state of a community during the recovery process, they may choose to realize some of the functionings. They may choose to cope with the lack of housing by, for example, going to a temporary shelter or moving out. They may choose to return, and if the situation, the conversion factors and the choice is there, choose to return and start working in schools or businesses, whatever their previous work was in the city. With this capabilities approach, we can further extend the FREC and IRE codes framework. And here is a San Francisco downtown example, now divided into 5 localities, for also to demonstrate some other features of the IRE codes framework in terms of interfaces. And another look at home reoccupation rates per different locality in the city, and one can see that they differ. But this is reflected on the individual's health indicators, assuming some occupancy of the buildings in these different localities. And we look at the well-being, the psychological needs, the mental health of the people, depending whether they're able to live in their own home, if they are in shelter, in tent shelters or in hard shelters, or with their relatives, and how they cope with the outcome of an earthquake. And you can see also that the recovery time of the housing is okay, but the recovery time of the individuals is yet longer and is somewhat slower than the recovery time of the infrastructure systems, showing us that this combined framework can not only provide a technical, but also the societal implications of a disaster in the city. And here is a video that we now have for a city in Switzerland, Basel, and a zip code in that city that we chose because of a certain characteristic of the buildings. They were all built right after the Second World War and share a certain vulnerability and exposure. And there was an earthquake of about magnitude 6.6 in Basel in 1356, and therefore we're simulating the effect of that earthquake on this zip code. And here you can see by how the change of the colors, which part of the impeding factors and the actual repair are these buildings undergoing. And as their recovery is being simulated on the graphs on the left, on the right, we see how the housing or home reoccupation is taking shape. There is a pretty long wait time of almost 3 months before the first homes are being able to be reoccupied. That has to do with the fairly long impeding factor sequence. We assumed some times for inspection, permitting, and design. But once the process starts, it goes. And here we see one of the aspects of what are the recovery resources and how the demand for recovery resources changes as the recovery process goes. We see that the demand for workers peaks at some point in time, probably is maintained at that level for quite some months, and then of course drops. But in a particular setting of the city, it is quite important to estimate what that demand may be, so as to contract people from outside areas that may not be affected by an earthquake, but able to work on the recovery of the buildings here. So this simulation and the other ones that I presented are made possible by software, of course. And the software that we're using is now Pythonized recodes, PyRecodes. It is open source. And here is a QR code for the link for that open source repository. And it is designed to model the recovery of a city and to quantify its resilience. The structure is object-oriented, of course, and we think has a fairly clear structure where users can adopt, input their own vulnerabilities and recovery functions, and look at their own models of infrastructure systems or adopt some open source models that we use, and compute the time evolution of certain parameters that are important for the performance aspects that they would like to investigate, both on the operational side and on the recovery resource side of a city. And with this software, we hope that this or some similar software that exists, that we can facilitate adoption of resilience-based design. But one other aspect of resilience-based design is what I need to address, and those are the resilience metrics. And here is the one that we have been using, the one that compares the system supply, the system demand, and computes the actual realized consumption of a particular resource, say electric power. And this area here, the blue area here, is the actual unmet demand, and integrated over time, we get a measure of the lack of resilience, a very similar measure to what had been proposed by many authors in terms of this area under the or above the swoosh curve, the resilience curve. But we also look at another simpler measure that is just time to recovery of a certain service level. And that is this duration that it takes to come back to a percentage of the previously available consumption here. This is a simpler measure and also importantly supported by the NIST 1190 document, where times to recovery in terms of short, intermediate, and long for many systems and facilities of a city have been proposed and looked at. And the percentages of where this is desired, the green boxes and the blue ones where it's estimated to be now, are an indicator that we have some work to do to improve the performance of our cities in terms of their resilience. But this format of time to recover is quite useful. And we can go further with IRE codes and do a probabilistic analysis of this resilience metric and others, starting with the probabilistic hazard assessment. A number of recodes runs for different disaster scenarios, aggregation of those runs, and the production of loss of resilience surfaces in this case, or time to recovery surfaces in this case, where if we set a goal of having, say, less than 20% of unmet housing demand 10 days after an earthquake, we can look at what is the state of the community's housing at the 10th day, and then ask ourselves, is this rate of exceedance, is this annual rate of exceedance acceptable or not for this particular community? And that way we can start formulating probabilistic performance goals related to resilience of a city, of a system of systems, considering housing, electrical power, water, cooling water, different aspects, different services, similar to what the NIST 1090 document prescribes. So multiple performance objectives formulated considering the resilience, the risks and the resilience of a city. And the framework that could be termed the resilience-based design framework starts with the performance-based framework, but does so multiple times to cover the housing instances and the infrastructure system components in the city, then brings them all together in the recovery module, where resilience is quantified and computed in various ways, but perhaps and most likely in terms of this time to resumption of service. And so we can think about the resilience-based framework of a city in a way that's similar to the performance-based framework for a structure. So one of these panels with performance objectives, hazard and functionality level needs to be repeated many times and integrated using a framework such as IRE codes to produce performance measures or resilience measures that we can now look in the NIST 1190 framework, for example, and evaluate if such a city is resilient enough. So we would start with the design resilience objectives, look at the current state or some future state of a city, thinking about some urban development in the future. Use a model to evaluate this design for resilience performance, and check if we're satisfied. We can also deploy measures to improve the performance of the city and test them. And I won't talk about them now, but they are definitely possible to imagine in terms of making the buildings less vulnerable through retrofits, or providing more resources to increase the rapidity of the recovery process. In this sense, we have, I hope I have shown you that it is possible to think about resilience-based design, and it is possible to conceptualize it based on what we know from performance-based design. Challenges remain. The cities are complex socio-technical systems. The resilience tools are now focused on technical aspects more than the societal aspects. We need to work on that. We need to provide better cost-benefit analysis benchmarks and tools such that such a resilience-based design can be more effective and more actionable. And then there is a bigger challenge. A city is a dynamic system. Over time, it changes. The environment changes, the hazard changes, climate changes. If you look at flood hazards, they will be bigger. The buildings age. The buildings get torn down and rebuilt for no reason related to any hazard, but just because of the urban development of that city. Technology changes. We are just about to start massively adopting electric cars. For example, how will that technology change the resilience aspect of the city? And so society changes itself. People age, young people come of age, their values are different, they care about different aspects of resilience, different aspects of function of the city, and therefore its resilience. But establishing this kind of a design loop that with resilience-based objectives evaluated at the level of the city is, I believe, possible. And I believe we need to continue working in this direction to make this resilience-based design actionable. With that, let me acknowledge the contributions of my students and colleagues at ETH, Nicola, Max, Lee, and Vesna, of course, and the students that are working at our Future Resilient Systems program in Singapore, in the NUS and Create Building, Lawrence and Hamed. So here is where I stop. I thank you, the audience, for listening to me, and let us go on to questions.
Okay, thank you very much, Professor Stojanovic, for this seminar. And since no one can applause, I record the applause so you can hear.
Thank you.
Good. All right, I'm gonna stop it. Okay, so now we're gonna start the session, which is called question and answer session. So we invite all people from the audience to write either questions in the chat, or they can simply raise their hands and I can unmute to allow them to talk. So let's see. In the chat, okay. And to get familiar, if there is anyone who is interested to speak, they should raise their hands. If I'm correct, so far I don't see any raised hands from home. So while probably either they are shy, or maybe it was so clear that everyone understood everything. And in any case, while we're waiting, oh, one raises hands. Okay, one moment. Trying to see where it is. Okay. Here it is, woman. You can speak. I allow to unmute. Oops. Yeah, you can speak, I guess, right now, right? I allow. Yeah, go ahead.
Hi, sir. It's Mohammed Jasmine here, sir. So basically, the question is about that which parameters are to be considered here in these resilient cities and constructive academics webinar, sir. Like the major one that we have studied in our bachelor's and in master, that these are the basic parameters like performance-based design. Which the basic parameters are to be considered as, sir, in your analysis
Can
pattern
you
methods.
can you say that
Yes, sir.
which
But yes, sir. Yes, sir.
can you repeat which
So
design which
yes, sir. In performance-based designs, there are basically three parameters we are uh, we are we have to be checked. Sir. Like the first one is SLE levels, sir, service level earthquake, and the second one is DBE level, sir, and the third one is NC level, sir.
yeah.
So in this, yes, sir. In this method, sir, which on which parameters, like so maybe there are some other parameters on which it is being done, sir. I'm a little bit confused about, sir.
So what if I understood correctly, what you're asking is which design parameters would one consider at the level of the city? And this is a question as big as the city. It is, of course, not easy to even do performance-based design on a building because there are a number of parameters that one could consider, as well as a number of different things that one can do. But at the level of a city, the options are even bigger. And so this is where engineers need to come to the city governance and to the people of the city with a portfolio of solutions. Some will be to retrofit buildings to some level. Others will be to remove dangerous buildings. Others will be to perhaps change the occupancy of some dangerous buildings. So all of those options exist. The same applies to infrastructure systems, elements of the power system, water system, transportation system, bridges, for example. So looking at this problem holistically is definitely a need. So there is no particular specific recipe that we can try do on a city level, such as, okay, we're going to look at a particular displacement in a particular structure. It will have to be the particular structure tasks need to be derived from the city level performance objectives. So for example, this one that there is a less than 20% of a need for housing, that the unmet demand for housing is less than 20% of the previously housed level. That performance objective can be disaggregated into performance objectives for particular types of buildings. For example, using a fault-free approach. This is what somehow with Mike Miller, Steve Main, Mary Kumeli, and Bob Budnitz, we looked at about 10 years ago or so. There are other ways to disaggregate such a city-level performance objective down to the individual buildings or elements of infrastructure systems. And to do that, one has to have a model of the integrated function of a city. And right now, with such a complex model, it's very difficult to invert it. It's very difficult to go backward and say, well, if I want this system level performance, here is my element level performance. So in this sense, the way is to do simulations and sensitivity analysis and to look at a particular city with a particular layout and decide what are the parameters to look at the level of individual buildings, at the level of individual infrastructure systems, in order that the city level performance objective, resilience objective is satisfied. So the question is a very, very good one, but there is no direct answer. In the same way that there was no direct answer as to what we should do to a building to make its performance good in 1995. There was a concept, and so some years later, we are at a good stage for performance-based design of individual buildings or structures. But some process for a similar process needs to be take place at the level of cities, and we are starting along that. And what I presented is one way to do it. There are several others. For functional recovery, there is the ATC 138 document. In terms of simulation, there is also the Colorado State NIST Center for Resilience with their in-core software. And those tools and those approaches are also possibilities for resilience analysis of cities.
Okay. So there is another
Thank
question
you.
now. Yeah. One moment. I am allowed to talk to Omar.
Hi, thank you so much, Gianpaolo. My name is Omar Kamou. I'm an assistant professor at TU Delft. I work on infrastructure resilience. I just joined the webinar quite late, so I hope I'm not asking the question that you already answered. So my question is that, can we do something about cities that haven't been designed to be resilient in the first place? Because there is path dependence here. There are decisions that we have taken in the past that are influencing our decision right now. So we have all kind of constraint and boundaries because of our previous decisions. Can we still redesign or design things that are already there in our environment?
Yes, thank you, Omar. This is another very important question because it is practically impossible to imagine that anywhere on Earth we will be designing a completely new city. Indonesia, new capital, Nusantara is a different example, but that's very, very unique that you start with an empty field. We always have to work with the fabric of an existing city. And what can be done? Let's take an example of the masonry, unreinforced masonry buildings in California. These were long recognized as dangerous, and since 40 years now, there is a provision in California law that requires that such structures be retrofitted. And whoever went there can see plaques on the sides of the building stating that this building is dangerous. There are only a few of them because over 30 years, owners and municipalities that own public buildings have taken steps to retrofit and reduce the risk of those buildings. This reflects on the resilience of the city too, very, very directly in that sense. Let's look again at, for example, water supply security, earthquake improvements that are going on in the city of LA through the change of water piping to a more flexible type into the San Francisco Bay Area, through the change of the type of water purification and processes tanks used in those facilities, from very fixed ones to more flexible ones. These measures, for example, including bridge retrofit sequences over there, are just examples of how a society can decide to tackle a systemic problem. No, the solutions are not going to be instantaneous. It is going to take decades to change the path of where the city has been going towards a more resilient one. But first of all, we can, with the help of hopefully what I presented today, what colleagues are doing in this area, realize what the continuing along the old trajectory would mean, and also test what new trajectories could possibly result in better performance. For example, one can do a simulation of a city that has been retrofitted in some way, whose vulnerabilities are smaller, and get an estimate of what the resilience of that city would be. And there, a cost-benefit analysis is needed. Exactly how to take into account the cost of time to do this is an open question. But yes, we can do it. It takes time, and we have to cost that time out too.
Thank you so much.
Hopefully, this kind of sort of gets in the direction of where you wanted to go.
Thank you so much. That's a very satisfying answer, to be honest.
Okay, thank you, Omar. So now I'm reading a question from the chat. They are asking, when assessing the building state for rebuilding or restoring, what should be the main aspect to consider first? When
assessing a particular building, I think that we have to look in two ways. One is this a unique building in terms of its construction and use? Is it a church? It is unreinforced masonry, most likely, or stone. but how important is it in terms of the cultural setting? If it is a very unique building, then yes, the strategies that are the steps to be taken are going to be very unique. There are colleagues who are looking at the restoration of historic monuments, and there you can find quite a wealth of experience and methods and also things to look at when those buildings need to be preserved. However, if the buildings are more typical, then we go back to the archetypes of buildings, and there we know, in some sense, from experience in previous earthquakes, what to look at. In Switzerland, here we have a code for evaluation and retrofitting of buildings. That is this Swiss Engineering and Architect Association, SIA code 269/8, that identifies a risk basis for evaluation and retrofitting of buildings, but also similar to ASCE 41, identifies what elements of the building and what performance aspects of those elements of the building need to be looked at. For example, out-of-plane stability of unreinforced masonry walls, drift requirements for brittle building systems, even reinforced concrete frames with poor transverse reinforcement, ability of the diaphragms to function, whether they are soft or stiff. So in a building, in a particular building that is more ordinary, I would go back to the archetypes, identify the archetype it belongs to, and then address typical failures of such a building. If you're looking at older cities in Europe, Italy, for example, in plane, out of plane, especially failure of masonry walls towards the top of the building, behavior of timber diaphragms in such buildings, and in many more modern buildings from the 60s and the 70s, brittle detailing in both steel and concrete structures. That's where I would look first.
Okay, so thank you very much. So I'm actually looking at the clock and I can see that we are running out of time. We're almost 1 hour now. So I would say that many of the additional questions you might find your answer inside our journal, Resilient Cities and Structure, as well as in the publication that Professor Stojalyvaner highlighted in his presentation. So I encourage you to watch your email in the following weeks because more webinars will coming out, and of course to publish and submit the manuscript to this new journal, Resilient Cities and Structure. And again, thank you to Professor Stojalyvaner for his contribution today. Thank you.
Thank you all very much. Thank you for organizing this, and thank you for listening.
All right. Bye, everybody.
All right. Thank you, Borja. It's a wonderful presentation. Thank you. Yeah.
And since Jasna is over here, she says hello, my wife.
Yeah. So hello and bye bye. Let's keep in touch and hope to see you on the World Conference very soon.
Yeah. That was what we're aiming for. Yes, thank you. Yes, looking forward to that.
Yeah. Thank you.
All right.
All right.
Okay. Thank you, Gianpaolo.
Bye. Bye, Borja.
Thank you, Quincy. Bye-bye.
Bye to both of you. Bye, everyone. Thank you.